Hey, welcome to the last lesson of the year. We're finishing up with the last section of Unit 10, where we're going to talk about a couple of algorithms that are unique in that they use recursion when solving a problem. There are two algorithms we're going to discuss, and one of them I'm going to assign you to actually code it, which is the second one, binary search. It's a pretty straightforward coding thing. It's not more than 10 lines really. Um, and I think from a quick lesson here, you'll understand what's going on and be able to do it. I am going to briefly describe merge sort. I'm not going to have you code this one. It's a bit much for distance learning like this. Usually I have students do it during class, but it takes a few days and it's kind of a thinker. Um, it's a really wild algorithm. So the idea with merge sort and any other sorting algorithms that go beyond bubble sort and insertion sort and um, let's see, insertion and selection sort is the other one that we have studied. Um, the runtime of those, as we may have discussed, it's pretty slow because they have to make so many comparisons because they're saying, okay, are these two, is this one bigger than this one? Then we move down one. Is this one bigger than this one? Then we move down one, and this one bigger than this one. And they just have to make so many comparisons that once you get into the, tens of thousands or hundreds of thousands of items that you're trying to sort, it becomes really, really cumbersome. So with merge sort, it uses recursion to break down the list of numbers into smaller and smaller groups and then shuffle them back together once they've all been split up. So I'm going to go through an example real quick. I've got 8 numbers here, and what this algorithm does is it recursively breaks down the set of numbers that's been given into 2 parts. Okay, and then eventually those parts get merged back together. So merging, think of merging like on a highway, where one car comes in, and then another car comes in, and we're kind of doing this alternating pattern. That's the idea here, is that we're going to try and do this alternating pattern of getting shifted back into place. So the algorithm works like this. We're given an array or a list or whatever of numbers, and we split it as best we can down the middle. Of course, if there's an odd number of numbers, we have to go one way or the other, but that's not. So we split the array, and then we call merge sort on each half of that array. So the initial array was called using merge sort, and then now we're going to call merge sort on each individual half of the array. So we call merge sort on the left half here, and so we call merge sort on 18, 2, 7, 10. And so what merge sort does is it splits it in half, and it calls merge sort on each half of that array. And so merge sort gets called on 18 and 2, and it gets split in half. And then once you're down to a size of 1, obviously you can't split that in half anymore. So that recursive tree ends, right? All our recursive functions have base cases, so that ends. And then what we'd do is it would go back up to the 7 and 10 and be like, oh, that one needs to be split apart. So we'll call merge sort on the 7 and merge sort on the 10, and those are then done as well. And now we need to work our way back up to the right side. So we're going to call merge sort on 9, 26, 14, and 3, which then gets split in half. And we're going to call merge sort on 9 and 26, which gets split in half. And then we'll call merge sort on 14 and 3, which gets split in half. So what is all the point of all this splitting? It is so we can identify partitions to then put back together. Okay, so what I mean by that was once we get done with all this splitting, then each call the merge sort then calls a helper function called merge. It's a separate function whose job it is just to take a set of numbers and put them back into their spots in the right order. So I'll show you what I mean here. The first call would be using the 18 and the 2, and we would give the 18 and the 2 that little partition to merge, not merge sort, merge. And we would say, merge, could you put these back together in the right order for us? And merge would say, well, which one's bigger, the 18 or the 2? Or which one's smaller, rather? And so it'd be like, oh, 2 is smaller. So it goes into the first spot in that little partition. And then the 18 is the only other number left, so I don't even have to do a comparison for that, which speeds up the process, right? So I'll have to do one comparison there. And then we move to the 7 and the 10, and we say, oh, which one's smaller? The 7, you get put there in that spot, in that partition, and then the 10 gets filled in. And then we do the same thing with these 4 numbers now. So these 4 numbers need to get put in place. What do you think we're going to compare? So we have 4 slots to fill. What 2 numbers do you think we'll compare here to compete for the first spot? So it's the 2 and the 7, right? Those are the only possible values that can go in that first spot. One of them has to be the smallest of this set of 4, because it can't be the 18 and the 10. We already know that those are not the smallest. So the 2 goes in first, and we move down. Now the 18 is eligible, but then the 7 beats it out, and so the 7 goes in next. And then we move to the 10. And now we're comparing 18 and 10. Which of those goes in? So we put in the 10, and then there are no more comparisons to make, and so the 18 gets filled into place. So we only had to make three or so comparisons there to sort those 4 numbers. We certainly did not have to compare 2 with 7, 2 with 10, 18 with 7, 18 with 10. Didn't have to do anything like that. So same process over here. The 9 goes in place, and then the 26 goes in place because the 9 is smaller. These are going to switch spots, 13 and 4, 3 and 14. And then we compare the 9 versus the 3. And so the 3 fills in, it gets crossed out. We move our counter over. And then the 9 gets compared to the 14 and goes in. The 14 gets compared to the 26 and goes in. And then finally 26 is just all that's left. And then our last step is now we have 2 sets of 4 numbers that are going to fill into our 8 spots. What do you think is going to get compared first? The 2 and the 3. When the 2 is the smaller, so it gets put in, our counter moves down. So obviously we would need a counter that's keeping track of where we're at in this bottom array as well, right? What spot are we about to fill? Position index 1, where we filled index 0. So we're comparing index 1 of this array versus index 0 of that array. So the 3 goes in, it gets crossed off, and so now we're down to here. The 7 versus the 9, so the 7 goes in. The 10 versus the 9 goes in. Whoops. The 10 versus the 14, the 10 goes in. The 18 versus the 14 goes in. And you can kind of see this merging pattern, right? It's not always going to alternate like it is here. That's just coincidence. Sometimes we'll have 2 or 3 in a row come from one side. It doesn't really matter. And then the 18 goes in and the 26 goes in. So that's how those get merged back together with as few comparisons as possible. Okay, so that was a sorting algorithm. With binary search, obviously we are now doing a search algorithm, not a sorting algorithm. And in particular with binary search, the data that we're searching through must be in order. I've talked about binary search a couple of times with you all. Usually I put it in the context of guessing a number from like 1 to 1,000. Or if I just asked you to guess a number from 1 to 1,000, you might guess 500, and I'd say, well, it's higher than that. So then you guess 750, and I say, well, it's lower than that. And so then you guess whatever is between 625. I can't do math while I'm talking. Anyway, you keep guessing in the middle and narrowing it down, and that way we don't have to go through all the values when we're searching, right? A linear search, we have to start at the beginning and go up, 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 up. Is it this? 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 And again, that's very time consuming. With our algorithms here, we're trying to speed things up with as few operations as possible. Doesn't mean less code, it means less operators. I mean, you can write a linear search with very few lines of code. That doesn't matter. What matters is how many operations we actually have to execute, because the linear search has to repeat a whole bunch of times. Binary search, we should be able to cut down by a lot because we're now doing a log-based algorithm. Log-based as in, if I have to search through 1,000 items, I only need to actually look at 10 of them, because 2 to the 10th is bigger than 1,000. We keep cutting this, the section that we're looking at, in half each time. So for instance, if I was looking for the number 10 in this set of numbers here, I would first look at it's always the middle number first. And here's how your function's actually gonna work in when you code this. You're gonna be sent a target value, which in this case will be the 10. You're gonna be sent an initial index and an ending index. So to kind of give you the range of values that you're currently looking at. These are gonna be indices, uh, not values. So 0 to 7 is our current search range. You'll find the middle index between those two values. So find the middle of 0 and 7, that should be relatively easy. In this case, we'll be looking at index 3, and we'll ask, is this 10? It's not. So what do? We're going to recursively call the search function again. This time, though, which section of our list should we be looking at, though? If our target value is 10, then we'll say, oh, well, it can't be in the later half of the array. It's got to be in the front half of the array. So the next time that we call our function, this time we will be looking at index 0 to index 2, right? We know it's not index 3. We already looked at that. If it was index 3, we would have been like, hey, we found it, index 3, done. That's one of our base cases. Remember, with recursion, we have base cases where we have to stop. That's one of them. One of the base cases is I found it. It was the middle value. In this case, it's not, so we are going to recursively call the function again on the left half of our list. So we're going to decrease our range by quite a bit here. Instead of 0 to 7, now just 0 to 2. And so we look at the middle value of 0 to 2, which of course is index 1. We ask, is that the target value? In this case, yes, it is. And we would immediately return that. Right? If we were looking for something else, let's say we're looking for 17. We would say, all right, is 17 equal to 10? No, it's not, but it's bigger than 10. So then we would call it again, and we would want to eliminate the 1 and go to the right of it. So we'd be like at index 2. So then we'd be searching from index 2 to index 2 when we called it the next time. And of course, when you search from index 2 to index 2, the beginning is 2, the end is 2. You're going to look at item 2 because that has to be the middle as well. You would eliminate that. And then when you called it the next time, if you attempted to move the indices now, then our front index and our end index would overlap. They'd be on the wrong side of each other. And that's how you know to stop looking, that you can just return -1 as your answer. Remember, -1 means we couldn't find it. It wasn't in there. So there are two base cases. Either you found the item and you return that index where it was found, or your beginning and ending indexes are on the wrong side of each other, so that you know that your search space has been completely diminished and there's nothing else to look at. So if you don't hit one of those two base cases, if there's still some area left to be searched, then you determine which half to search. So like, let's say we were looking for the number 48. We would have said, oh, 48 is bigger than 38 because I'm going back to the original value. And so then we would have narrowed our search down. Instead of 0 to 7, we would have narrowed it down to 4 to 7. Okay, so whichever side needs to move, we're going to move it up past the initial middle. Okay, so you'll have to think about the math that you want to do there. Finding the middle index, pretty easy. You're just going to find the average of the beginning and the end. Right, so our very first time we said, all right, the beginning is 0, the ending is 7, the average when we round down is 3. And then if you figure out that the value is bigger than what's at spot 3, now you're saying, okay, well, let's call it again with 4 and 7. Okay, so where's that 4 going to come from? Right, can you tell that we're going to move it past the middle, shrink it down to the right side, and then we're given 4 and 7. We're like, ooh, now the middle of that now is 5. You got to choose 5 or 6, and if you round down, it's 5. And if it's bigger than that, now you're saying, all right, let's search 6 to 7. and you do that in the middle